Namaste. Welcome to lecture series on Mastering Bioprocess Engineering Numerical Solutions from Pauline M. Doran's Bioprocess Engineering Principles. In the previous videos, I have given explanation for solved examples available in the book, and also I have solved 5 unsolved problems which are available at the end of the chapter, that is 2.1, 2.2 and 2.3. These are the problems which are involving unit conversion, and to problem 2.4 where we had some sort of unit conversion as well as time calculation, and fifth problem we were solved Reynolds number at 2 different cases. Today let us proceed and solve few more problems. Next is problem 2.6 is a property data. Basically this problem need not to be perform any calculation. It is a very important problem where we need to understand how to retrieve various physicochemical properties of given compounds. We come across lot of calculations where we require some physicochemical data of the molecules or compounds which involved in the process, and there are a lot of handbooks are available to obtain this particular data. As I told in previous videos also, you no need to remember all the units, dimensions, or you no need to remember the physicochemical properties of all the compounds. So we have lot of data books are available, or even websites are available. These websites will help us to retrieve the data, or basically the physicochemical properties of various molecules or components. One such popular book used by chemical or biochemical engineers is Perry's Chemical Engineers Handbook. Presently 9th edition of this Perry's Chemical Engineering Handbook is available. Here in this problem 2.6, the property data, using appropriate handbooks, find the values of, there are 5 sub questions are there. In the first sub question we need to retrieve the viscosity, next diffusivity, thermal conductivity, density and specific heat. So we need to retrieve these particular data from the handbook. So make sure you reference the source of your information and explain any assumption you make. So if you are making any assumptions while retrieving the data, we will see that, we will understand in the later stages. So what reference we are using, as I already told, we are going to use, or we are employing Perry's Chemical Engineers Handbook, and here I am using 8th edition which is published by McGraw-Hill publication. And let us move to the first part. What is the first part? The viscosity of ethanol at 40 degree centigrade. So if you go to this Perry's Handbook, that is 8th edition, page number 2428 and table number 2313, where the viscosity of organic, inorganic and organic liquids are given, and the values are given in Pascal second. So when you calculate the viscosity, you will not directly get the viscosity in this particular table. You get a constant, and using that constant and temperature we are going to understand, so what is the viscosity of that particular parameter. So here what happens, if you see this particular table, what is the molecule it is asked? It is ethanol. So if you see here, ethanol is there, 126 component, and it is given, the molecular formula is given, and CAS number, chemistry abstract service number is given, molecular weight is given, you can notice molecular weight is given, and also the constants are given, that is C1, C2, C3, C4 and C5. These constants are given, and minimum temperature, maximum temperature in which you can use this particular constant is also given. So we are supposed to use this particular equation. It is given at the bottom, that is mu is equal to exponential C1 plus C2 by T plus C3 ln T plus C4 T to the power of C5. But if you see this particular ethanol component, we are having only C1, C2 and C3. So we can ignore the remaining terms. So if you do the calculation using this particular equation, it is just a substitution problem. You don't need to do great mathematics here. So C1 you have to substitute, C2 by T. So what is this basically T? Here also it is mentioned T must be substituted in Kelvin. But in the problem statement, it is given as 40 degree centigrade, and we know how do we convert this centigrade to Kelvin. That is, we need to add 273.15, we end up with 313.15 Kelvin. So T is 313.15 Kelvin, and we substitute, you can easily substitute here, that is exponential. Here the C value is nothing but, you can see here, that is C value, this is the C value, this is the, this one, no sorry, not the below one, this one. So what is the C value? That is 7.875 plus, that is the next value is 781.98 divided by 313.15 Kelvin plus C3. What is C3? That is minus 3.0418 into ln of 313.15. So if you do the calculation, so you are going to obtain the value of 8.18 into 10 raised to minus 4. Mu is equal to 8.18 into 10 raised to minus 4. What is the unit? As it is told, it is nothing but Pascal second. If you want to convert it to other units, you can easily convert it. For example, you want to convert it to centipoise, multiply by the conversion factor. There is one more method called as nomograph. This is also very simple method. What does this nomograph is? You have, this is called x-axis and this is y-axis, and this is your viscosity value, and here it is temperature. Here this is temperature in degree centigrades. How do we get the viscosity value? You can notice here in this particular table for that is 318, table 2 318, it is in page number 448. It is given viscosity of liquid coordinates for use with figure 2.32. This is 2.32. So how do we get the viscosity value? Here for ethyl alcohol, we assume that ethyl alcohol is 100%. So it is x value is 10.5, 8 value is 13.8. So x value 10.5 means this is 10, 11. So this is 10.5. You can go here, and 13.8 approximately it comes here. So this is the point. Now 40 degree centigrade, this is the 40 degree centigrade. So we need to draw a line joining this particular two dots. So the touching this particular viscosity line. So I will just plot a line here. So it can go, you can take a print copy and you can draw a line. So you will end up with the approximate viscosity value, that is mu is equal to 0.82 centipoise, and also it is given at the bottom. If you see, if you can zoom this video and you can check this. So it is, if you want to have a unit in Pascal second, then you have to multiply it by 0.001. You will end up again, that is previously we got 8.18, here you are going to get 8.2 into 10 raised to minus 4 Pascal second. I hope these two methods, one is using a table, other one is using nomograph. So next part B, we go to the part B. What is this B? The diffusivity of oxygen in water at 25 degrees centigrade and 1 atmospheric pressure. So it is given here, the diffusivity of liquids at 25 degrees diffusivity in liquids, the gas in liquids. So the diffusivity at 25 degrees centigrade and 1 atmosphere, and here you can directly get it as oxygen. It is diffusivity in water. You can easily get it as 2.5, that is diffusivity value is nothing but 2.5 into 10 raised to minus 5, 2.5 into 10 raised to minus 5 centimeter square per second. So don't get confused. So this is D into 10 raised to 5 is equal to 2.5. So D is equal to, if you take this side, so it becomes D 2.5 divided by 10 raised to 5. That is the reason it becomes 2.5 into 10 raised to minus 5. Don't read it as 2.5 into 10 raised to 5. If it was comma, then we were just multiplying the number. For example, if it was something like this, D comma 10 raised to 5, then I can read it as 2.5 into 10 raised to 5. But in this case D into 10 raised to 5, so it becomes 2.5 into 10 raised to minus 5 centimeter square per second. So this is the solution for B. Next one, solution for C. The thermal conductivity of Pyrex borosilicate glass at 37 degree centigrade. So yes, it is given in page number, that is table 326. Table 326. In this the properties are available. It is given, what is the given? Temperature between 30 to 75 degrees centigrade. You can use this in the range of, it is given here where it is available, glass, and this is borosilicate type glass, and the range between 30 to 75. Here for us it is asked at 37 degrees centigrade. The value of thermal conductivity is the K is equal to 0.63 and unit is given, that is BTU per hour feet square into Fahrenheit per feet. This is the unit for K, that is 0.63. So in this temperature range, even if it is 60 or 50 or 68, whatever it is temperature in the range, so the thermal conductivity will be 0.63, and this is the unit, and you can convert later into whatever required unit you wanted for further calculation. So the next sub question is the density of acetic acid, at 20 degree centigrade, the density of acetic acid at 20 degree centigrade. So if you see this table number 2108, this is basically for density of acetic acid, and here the this is 20 degree centigrade, this particular column is 20 degree centigrade, and if you see at the end, you can notice here this is basically for 100%. There is no percentage is not given what percentage of acetic acid. So we can easily assume that it is 100% acetic acid. For 100% acetic acid it is 1.0498, and if you see the bottom, the units are given, that unit is nothing but rho is equal to 1.0498 gram per centimeter cube. This is the density of acetic acid. So what is the next question? That is specific heat capacity of liquid water at 80 degree centigrade. So now what happens? This is the table, the property table for thermodynamic property of water. In this table it is given, the specific heat of water is given. You can easily understand this is Cp, a specific heat of water is given. Using this particular value, you can easily get it. Now what is the problem here is, if you notice that what is we are supposed to ask at 80 degree centigrade, temperature is equal to 80 degree centigrade, but this is in Kelvin, so let us add 273.15. If you add 273.15 to this one, you end up in getting 353.15 Kelvin, 353.15 Kelvin. Now if you see in this particular table, 353.15 Kelvin is not there. There is a value for 350 and there is a value for 360, but there is no value for 353.15. So what we are supposed to do, we go and employ something called as interpolation. So we can interpolate the data between these two data sets and we can obtain the value at 353.15. So what is the formula for interpolation? That is mu at 80 degrees centigrade, or mu at 80 degrees centigrade, or 353.15 Kelvin. So we know what is the mu1 now. Mu1 is at 350 Kelvin. So mu t is nothing but 360 Kelvin. So what is now the mu1 value? So at 350 Kelvin, this is not mu, this is Cp. Sorry, this is not mu, this is Cp. Don't get confused. This is Cp at this is Cp1, Cp2 and Cp1. So now if you see what is the value at 350 Kelvin, that is Cp is equal to 0.075567 kilojoule per mole Kelvin. So at 360 Kelvin, the value is 0.075708 kilojoule per mole Kelvin. So now we have two equations. we can easily substitute into this particular formula, and let us see what value we are going to get it. 53.15 Kelvin is equal to, so we need to substitute at 350 Kelvin, that is 0.0755667, that is kilojoule per mole Kelvin, plus temperature, that is 353.15 T minus T1, that is 350 Kelvin divided by, that is 360 Kelvin minus 350 Kelvin. Okay, anyhow all this Kelvin get cancels, so into, that is 0.075708 minus 0.075567 kilojoule per mole Kelvin. If you do the calculation, you end up in getting 0.07561 kilojoule per mole Kelvin. So if you notice this, the value is in between the two values, that is at between 350 and 360 Kelvin. This is basically dimensionless group and property data. So we need to basically retrieve some data from the handbook, and we need to employ here, and we need to perform the calculation. So what is the problem statement is, the rate at which oxygen is transported from a gas phase to liquid phase is a very important parameter in fermenter design. A well known correlation for transfer of gas is SH is equal to 0.31 GR to the power of 1 by 3 SC to the power of 1 by 3. What is this SH? It is called as Sherwood number. Basically these are used in mass transfer, that is Sherwood number. GR is the Grashoff's number and SC is the Smith number. So, and also these are all dimensionless number, means there is no dimension for them. These dimensionless numbers could be defined by using this particular equation, that is Sherwood number could be calculated as KL into dB divided by D. This is the diffusivity, and this is the bubble diameter, and KL is the mass transfer coefficient. And also like same like this Grashoff's number could be calculated. Rho L is the liquid density, rho G is the gas density, and also SC, that is the Schmidt number, could be calculated by mu L, that is the liquid viscosity, liquid density and diffusivity. Here the definitions, the explanation for each parameter is given. A gas sparger in a fermenter operated at 28 degrees centigrade and 1 atmosphere produces a bubble of about 2 mm diameter. Calculate the value of mass transfer coefficient KL. Collect the property data from for example Perry's Chemical Engineer's Handbook, and assume that the culture broth has properties similar to those of water. This is very important. And also he is telling, do you think this is the reasonable assumption? Report the literature source for any property data used. State explicitly any other assumptions you have made. So this is very important, because if the property, what type of liquid, if it is not given, so it is well known the fermentation we employ water as a main solvent, but many times what happens, even though we use water, maybe sometimes we come up with something called high viscous solutions. For example, you see something xanthan gum solution, or example like that, where maybe sometimes we use very low viscosity solutions. But if we, here in this case what he is telling, assume this fermentation media or whatever the broth is having water properties. For me it is very easy now, I can easily assume, so oxygen, the gas is oxygen, it is getting transferred in the media, that is nothing but water. So let us see step by step and how can we solve this particular problem. Problem 2.7. So from Perry's handbook, from Perry's Chemical Engineering or Chemical Engineer's Handbook, so the diffusivity of O2 at 25 degrees centigrade and 1 atmosphere pressure is 2.5 into 10 raised to minus 5 centimeter square per second. So just now in a previous problem also we got this particular value, that is at 25 degrees centigrade 2.5 into 10 raised to minus 5 centimeter square per second. So as the temperature difference is not too much, in the problem statement as temperature is 28 degrees centigrade, here the given temperature is 28 degrees centigrade. So we can easily assume 28 degrees centigrade, again 1 atmospheric pressure, we assume the same value. So the diffusivity is nothing but 2.5 into 10 raised to minus 5 centimeter square per second. I hope you understood. So just temperature difference is very small, so we can assume the same diffusivity value for this 28 degrees centigrade also. And one more statement he has told, that is as fermentation medium is mostly water, so it is reasonable to assume the density of liquid in the fermenter is the same as that of water. Assume, reasonable to assume the viscosity of liquid is also same as what? Okay, it is not high viscous liquid, for example gum solutions and all. So if it is of normal viscosity, or like you can easily assume, reasonable to assume it as water viscosity. And again from Perry's handbook, Perry's chemical engineer's handbook, you can get at 28 degrees centigrade, the viscosity of water, or now we are assuming that fermentation broth is nothing but water, it is nothing but 0.9963 gram per centimeter cube. So and also the viscosity at 28 degrees centigrade, it is mu L is equal to 0.87 centipoise. So now we need to like calculate the density of gas, okay, or oxygen, that is the density, because we need rho g in calculation of Grashof number, we need rho g. So density of gas could be easily calculated because we know the temperature, we know the pressure, so we know the you can assume it as 1 mole, and we can easily calculate the molar density, and this molar density we can convert directly into the regular normal density. So let us use the density of O2 at 28 degrees centigrade and 1 atmosphere pressure can be calculated by ideal gas. What is this ideal gas? That is PV is equal to nRT. So we know the definition of molar density. What is molar density? Molar density is nothing but N by V. N by V is the molar density. So now we can rearrange this equation. Even this equation is available at equation 2.35, the page number 30. Page number 30 you can get this equation. So we can just rearrange N by V is equal to P by RT. Temperature in ideal gas equation is in absolute temperature, that is in Kelvin. So how do we convert? That is T Kelvin is nothing but T degrees centigrade. These are all very basic things, just I am writing for your reference. So now the value given is 28 degrees centigrade plus 273 Kelvin, 273.15, which yields 301.15 Kelvin. Again from appendix B, you can easily get the R value, that is nothing but 82.057 centimeter cube atmosphere per Kelvin gram mole. So we have all the data that are substituted, that is rho g, we can write it, that is molar density, that is N by V is equal to 1 atmosphere divided by 82, that is that's what we just rearranged, right? N by V is equal to P by RT, that is 82.057 multiplied by 301.15 Kelvin. The unit of R is centimeter cube atmosphere per kg, sorry, Kelvin gram mole. So this atmosphere cancels, and this Kelvin cancels. So if you do the calculation, you will end up with 4.05 into 10 raised to minus 5. This gram mole goes to the numerator, gram mole per the centimeter cube in denominator, gram mole per centimeter cube. So generally what happens, density kg per meter cube, the regular density, now gram mole per centimeter cube, it is a molar density. Now using the atomic weights, you can calculate the molecular mass of oxygen, that is molecular weight of oxygen is nothing but, molecular weight of O2 is nothing but 32. Now this particular rho g, that is 4.05 into 10 raised to minus 5 gram mole per centimeter cube. So we know that 1 gram mole of oxygen is nothing but 32 grams. So if you do this calculation, you will end up with 1.3 into 10 raised to minus 3 gram per centimeter cube, 1.3 into 10 raised to minus 3 gram per centimeter cube. So now the given viscosity whatever we obtained, it is in centipoise. So that also we need to convert into gram per centimeter second. So if you take this from table A9 in appendix A. So we know that 1 centipoise is nothing but 10 raised to minus 2 gram per centimeter second. And also from equation 2.17, that is in page number 22. So G is nothing but 980.66 centimeter per second square, and also we know 1 centimeter is equal to 10 mm. 1 centimeter is equal to 10 mm. So now let us convert this particular all the units into using values, the parameter values, and conversion factors could be used to calculate the dimensional groups in the equation. So now let us first convert into consistent units, because viscosity and bubble diameter all are in different units. So let us convert into the viscosity, that is mu is equal to, we have 0.89 centipoise. So let us convert it. 1 centipoise is nothing but 10 raised to minus 2 gram per centimeter second. So if you do the calculation, it is 0.89 into 10 raised to minus 2, this is 87, I think 87, 10 raised to minus 2 gram per centimeter second. So bubble diameter dB is given as 2 mm. So let us convert it into centimeter. So 1 centimeter is nothing but 10 mm. So it becomes 0.2 centimeter. So we have all the units in the consistent units. So let us start calculating one by one. So let us calculate the Grashoff's number. The Grashoff number, the definition is nothing but dB cube rho g into rho L minus rho g into g divided by mu L square, So let us substitute all the values, that is 0.2, it is 0.2 0.2 centimeter whole cube. So next rho g, it is nothing but 1.3 into 10 raised to minus 3 gram per centimeter cube. So next one rho L, it is 0.9963 gram per centimeter cube minus 1.3 into 10 raised to minus 3 gram per centimeter cube, and again we need to multiply it by 980.66 centimeter per second square. So divided by the whole term, we need to divide it by 0.87 into 10 raised to minus 2 gram per centimeter second whole square. You can cross check it. So whether all the units gets cancelled, definitely it gets cancels. All the units, once it is cancels, you are ending up with the value of Grashoff number is 134. If you want to check the consistency, you can check whether we get a dimensionless number or not. That is centimeter cube into gram per centimeter cube into gram per centimeter cube into centimeter per second square. So divided by, we have gram square per centimeter square per second square, gram square per centimeter square per second square. So now this gram per centimeter cube, gram per centimeter cube, so all these values get cancelled. If you notice that all these units, because here you can notice centimeter cube, centimeter square, this get the centimeter cube get cancels, right? The gram, this becomes gram square, this gram get cancels. Here centimeter cube is there in the denominator, it comes to denominator, this goes to numerator, this centimeter square, centimeter, so all these values get cancelled. This is nothing but dimensionless number. Please write it again and you try to check whether the Grashof number is dimensionless number or not. So similarly you can for Schmidt number that is given, S is nothing but mu L divided by rho L into diffusivity, Let us substitute the values, that is 0.87 into 10 raised to minus 2 gram per centimeter second divided by 0.9963 gram per centimeter cube into 2.5 into 10 raised to minus 5 centimeter square per second. So you are going to get the value as 349. Again you can check the consistency, that is gram per centimeter second multiply by this one, it goes to numerator, that is centimeter cube per gram into second per centimeter square. So all get this becomes centimeter cube, this gram get cancelled, second get cancels, again you end up with dimensionless number. So therefore so now we can calculate, that is the correlation between Sherwood number, Grashof number and Schmidt number is given as SH is equal to 0.31 Grashof number to the power of 1 by 3, Schmidt number to the power of 1 by 3. Let us substitute, we know the values, let us substitute the values, that is it is nothing but 0.31 into 134 to the power of 1 by 3, 349 to the power of 1 by 3. If you do the calculation, you will end up with 11.16. So the Sherwood number is equal to 11.16. We know the definition of Sherwood number, that is nothing but KL dB divided by diffusivity is equal to 11.6. So let us rearrange this one. The KL is equal to 11.16 multiplied by diffusivity divided by the dB, the bubble diameter. So we'll substitute it, 11.16 into 2.5 into 10 raised to minus 5. This is again centimeter square per second divided by the bubble diameter is 0.2 centimeter. So if you do the calculation, you are going to get it as 1.395 into 10 raised to minus 3 centimeter per second. The KL value is, this is the value. A simple substitution, basically this is not a complex problem, we need to get the data from the data book. So why this problem is important? Because making some assumptions are very important when you do any bioprocess calculation, because every data will not be given in the problem. Sometimes we need to assume suitably the required data, but your assumption should be proper. So why you are assuming that particular value, particular case, you need to understand that and you need to write it in this particular solution. Let us move to the next problem, that is problem 2.8. It is dimensionless numbers and dimensional homogeneity. So we all of us know the dimensional homogeneity is nothing but whenever we have any equation, for example here the Colburn equation is there, the units of right hand side must be equal to the units of left hand side. So and mostly if you see, all of these are again dimensionless numbers. This is again one dimensionless number and this is one dimensionless number and this is one dimensionless number, so that you can easily evaluate any parameter. So in this question basically asked is the Colburn equation for heat transfer is where this is the equation where Cp is the heat capacity, the unit is BTU per LB degree Fahrenheit, mu is the viscosity, that is pounds per hour for feet, and K is the thermal conductivity, the unit is BTU per hour feet square, degree Fahrenheit feet inverse, and D is the pipe diameter that is in feet, and G is the mass velocity per unit area, that is pounds per hour for feet square, and the carbon equation is dimensionally consistent, means it indicates that the right hand side units are equal to left hand side unit. What are the units and dimensions of the heat transfer coefficient H? So, let us evaluate one by one. So, let us see the solution for problem 2.8. Problem 2.8. First, let us evaluate the units of the groups. So, first let us evaluate problem 2.8. First, let us evaluate the units of groups. What are the groups? That is Cp mu by K and dg by mu. So, first let us evaluate what is the unit of these two groups. Okay, this is one group and this is one group. So, units of Cp mu by K. So, nothing but what is the unit of Cp? It is given in the problem itself, that is BTU per LB, that is pound degree Fahrenheit. So, multiply by the viscosity, that is viscosity is LB per feet hour, and the unit of K. So, what is the unit of K? So, as I told the simplified form, if you write down the units of K, in the problem statement the unit of K is given as 1 divided by, I will write 1 divided by, that is BTU per hour per feet square. So, multiply by degree Fahrenheit feet to the power of minus 1. Okay. So, per feet, this is per feet to the power of minus 1. So, if you do this like cancellation of all the units, so here basically what happens, this pound get cancels, BTU get cancels, and this degree Fahrenheit, this is the basically this inverse indicates that this term can go to the numerator. So, degree Fahrenheit get cancels. So, this BTU got cancels. So, and this hour, this again this is in here in this case it is in denominator, means if you take this up it goes to numerator, this hour gets cancels. So, basically all the units gets cancels and you end up with 1. 1 indicates that all the units got cancelled, and this group is dimensionless. Please check it, calculate the dimensions once again and check whether you get 1, that is dimensionless. Again let us calculate the units of dg by mu. So, what is the unit of d? That is feet, okay, and g that is mass velocity per unit area, that is Lb per hour feet square divided by the viscosity unit, that is Lb per feet hour. So, this again this feet goes to the numerator, feet square get cancels, hour get cancels, Lb get cancelled. So, you end up with again 1. So, the unit of these two groups is nothing but 1, means it is dimensionless. So, we can write therefore these groups are dimensionless. So, for equation to be dimensionless, dimensionally homogeneous, so what happens, this H by CPG, this particular term must also be dimensionless. So, based on this fact we can easily understand. So, what happens, H by CPG is equal to 1, we can easily rearrange this. So, H is equal to Cp into G. So, I will again tell you, this is the basically this part is the carbon equation given, H by Cpg, this is one term, and second term is Cp mu by K to the power of 2 by 3 is equal to 0.023 divided by dg by mu whole to the power of 0.2. So, now we know this is 1, okay, means 1 indicates a dimensionless, and this is also dimensionless. It means that this term also must be dimensionless. If it want to be homogeneous, the equation, so this term also should be dimensionless. Dimensional indicates that, so all the units gets, the H unit get cancelled with Cp into G, so we end up with 1. So we can just rearrange to get the units of H. So let us have the units of Cp and G, that is units of H is equal to units of Cp into G. So what is the unit of Cp? That is BTU per LB degree Fahrenheit multiplied by LB per hour feet square, LB per hour feet square. So now what happens, this the term, whichever term we could get cancels, let us cancel this one and we end up with BTU per hour degree Fahrenheit hour into feet square. So this is the unit of H. This is the unit of H. So this LB get cancels. A unit of H is BTU per degree Fahrenheit hour feet square. So let us understand what is the dimension of this, and we got the units. So basically what is happening, what are the units and dimensions of the heat transfer coefficient H. So now we got the dimension like unit. So let us write the dimension of this particular term. Now we can just easily deduce the dimensions from this particular equation from table A7, again in appendix A. So BTU is a unit of energy. We know that British thermal unit is a unit of energy, and with dimension, so is nothing but is equal to L square m T power minus 2. L is length, mass, and like a time, that is T power minus 2. And also degree Fahrenheit is a unit of temperature, So which from table 2.1, the dimensional symbol is theta. So because time and temperature, if you write T, both become same, so it is temperature generally represented by theta. And H is again hour. H is hour, is a unit of time with a dimension T. And again feet is a unit of length, and dimension is L. So let us substitute into this units. So the dimension of H is equal to BTU, let us write L square m T power minus 2 theta per theta, then T inverse, this is for time and this is for feet length. So if you all the units, if you cancel them, so this because L square L power minus 2 get cancels, then becomes m T power, this minus 2 minus 1 become minus 3 theta inverse. So this is the dimension of H. So hope you understood from this. Just this, we no need to use this particular, we no need to calculate whether they consistent or not, but basically why we are identifying the units, whether we need to understand whether dimensionally the equation is consistent or not. We can understand from this one, and then we can evaluate the H terms. Hope you understood this particular problem. So let us move to the next problem. The problem 2.9, it is again based on dimensional homogeneity. Here the problem is the terminal eddy size in a fluid in turbulent flow is given by the Kolmogorov scale, that is lambda is equal to V cube divided by epsilon to the power of 1 by 4, where lambda is the length scale of the eddies, it is in micrometer, and sigma is the local rate of energy dissipation per unit mass of fluid, that is watt per kg. Using the principle of dimensional homogeneity, what are the dimension of the term represented as V? So what is the meaning of dimensional homogeneity? As I already explained, means the units of right hand term is equal to the units of left hand term. So both the side units are same based on this principle. So if you can understand whether it is like homogeneous or not, then we can easily evaluate the units of the rest of the parameters. So let us see the solution for this problem. Problem 2.9. Problem 2.9. So lambda, as I told, from the unit we can easily understand as dimension because it is given micrometer, dimension of L, and sigma as unit watt per kg, watt per kg. Therefore from table A8 and A3 in appendix A3 and A8 and A3 in appendix A, the dimension of sigma are L square m t power minus 3 m inverse. So this is for watt and this is for kg. Okay, so watt per kg. So if you kind of simplify this one, the unit becomes L square t to the power of minus 3. So this is for watt and this is for kg. So you can see that sigma, it becomes L square t power minus 3. So let us substitute this information into the equation for lambda, for dimensional homogeneity T. So L is equal to, this is a dimension of this particular lambda. So dimension of V divided by the dimension of that epsilon is L square t power minus 3. So whole power 1 by 4. Whole power, why? Because lambda is equal to V cube, this is V cube, sorry, this particular term is V cube. So V cube divided by epsilon whole to the power of 1 by 4, whole to the power of 1 by 4. So now L is equal to this dimension of V to the power of 3 by 4. If you multiply 1 by 4, it becomes 3 by 4 divided by L to the power of 2 by 4 into t to the power of minus 3 by 4, because we are just multiplying. So now what happens? We can just substitute this particular L, we can bring it this side. So now dimension of V to the power of 3 by 4 is equal to L into L to the power of 2 by 4 into t power minus 3 by 4, 2 power minus 3 by 4. And this particular term, it becomes L to the power of 3 by 2 and t to the power of minus 3 by 4, because this one you can write it 1 plus 2 by 4. If you do it, you can easily calculate 6 by 4, it becomes 3 by 2. So that is what you have got here, that L to the power of 3 by 2 t power minus 3 by 4. So this is V to the power of 3 by 4. So for V, what will happen? You can just write it like this, L to the power of 3 by 2 into t to the power of minus 3 by 4. So this is 3 by 4 whole to the power of you can just 4, it becomes 4 by 3, it becomes 4 by 3. So now if you just multiply this one, V is equal to L to the power of 3 by 2 into 4 by 3, t to the power of minus 3 by 4 into 4 by 3. So this get cancels. So now it becomes minus 1. So basically what will happen? It becomes L square. So this is 4 divided by 2, this becomes L square t power minus 1. So this is the unit of V, V based on this dimensional homogeneity. Problem 2.10 is again dimensional homogeneity and GC term, that is a conversion factor, and two students have reported different versions of dimensionless power number NP used to relate the fluid properties to the power required for stirring. So two equations are given, so one with just G, another one with the GC, where P is the power, G is the gravitational acceleration, rho is the fluid density, Ni is the stirrer speed, Di is the stirrer diameter, Gc is the force unity bracket. Which equation is correct? Problem 2.10. So, let us write the dimension of each parameter. So, the dimension of Di is nothing but length, it is nothing but L. So, from table 2.2, in the book you can check the table 2.2, the dimension of P is nothing but L square m t power minus 3, and the dimension of rho, the density is nothing but L power minus 3 m kg per meter cube. So, a meter cube L into L into L, the L power minus 3 into m. So, dimension of G, that gravitational constant, in nothing but L to the power of t minus 2. So, you can check for section 2.3, this is given, and dimension of rotational, that is nothing but a speed, rotational speed is that is Ni. We know that it is per time, that is T inverse. So, you can also check this in section 2.1.2, you get it. So, therefore, so let us see one by one equation. Dimension of P G divided by rho Ni cube Di to the power of 5. So, let us substitute the dimension of each parameter, that is L square m t power minus 3, this is for P, L t power minus 2 divided by the density L minus 3 m t inverse, that is power 3 L to the power of 5. So, let us simplify this particular term. So, now what happens? This become L cube, L into L square into L, this become L cube, and this, let us cancel this m and m, and a numerator, that is t power minus 5, it happens minus 3 minus 2 minus 5 divided by, so if you take this L power minus 3 L power 5, this term you can just retain it, it becomes L power, let us substitute minus 3, and this become t power minus 3 and L power 5. So, further simplification, that is L power 3, and this particular t power, this 3 goes to numerator, it becomes t power minus 2 divided by minus 3 plus 5, it becomes L square, and again if you take this to numerator, it becomes L t power minus 2, because 3 minus 2, it becomes L t power minus 2. This is the dimension we have got for this particular NP number, that is the equation whatever you have for NP. So, this NP is a dimensionless number, NP is a dimensionless power number, but we are getting unit as L t power minus 2. Obviously, this equation is wrong, So, let us check one more equation. So, if you take as NP, as I told, NP is a dimensionless number, so it is not dimensionally homogeneous, so therefore, it cannot be correct. So, let us move further from section 2.3. So, the dimension of GC is equal to 1. Dimension of GC is equal to 1. So, let us substitute it, that is P GC divided by rho Ni cube Di to the power of 5. So, it is nothing but L square m t power minus 3, this is 1 divided by L power minus 3 m t power minus 3 L to the power of 5. So, all the term get cancels, you are going to get 1. So, means obviously the power number, a dimensionless power number does not have any units, it becomes 1. So, we can easily understand. So, this is dimensionally homogeneous, that is equation 2 is dimensionally homogeneous. So, therefore, can likely be correct. Thank you for watching. Please do not forget to subscribe.